Hello, my name is Benjamin Wright. I'm a high school senior currently in Phillips Exeter Academy, and I'll be going to MIT next year. So I've been doing competitive math for almost my whole life. In middle school, I went to MATHCOUNTS Nationals, got 5th place from Texas. And in high school, I've gone to Blue Mop twice. And yeah, it's my pleasure to be teaching you today, as when I was younger, other people were able to teach me as well. And I always appreciated them, and I hope you'll learn something out of this as well. So the topic of today is similarity. Similarity is an important part of geometry, and it comes up all the time. So let's move over to my PowerPoint slide. So similarity. So what is similarity? Two shapes are similar if they're the same type of shape, but just maybe possibly resized, reflected, rotated, moved. You can do anything to it as long as it kind of looks the same. That's like a really non-rigorous way of explaining it. If you want to be more rigorous, you can describe similarity by, if you have two figures, you make each point correspond to another point, and those corresponding points must have exactly the same angle, and the side lengths, the corresponding sides, can be scaled up by a certain ratio. So if you look at this red polygon and this blue polygon, they are similar with a scale factor of 2. All the angles are the same, and all the side ratios are the same. So notation, when you describe two shapes as similar to each other, there's a very specific way you write it out in math. And that'll be over here. You write the two polygons with this squiggle in between them. And that seems simple, but actually you have to pay very close attention to the order. The order of each point determines which points correspond to which. For example, the first letter here is C and the first letter here is N. And that's because C corresponds to N here. They have the same angle or in the same location of the two shapes. And we can move on. Second letter is D here, second letter is P here. So D corresponds to P, and we can keep going. E goes to Q, A goes to L, and B goes to M. And that matches the order. So pay very close attention to the order that you write them down. And here is, we get to triangle similarity. You can actually have similarity between any two shapes. They don't actually have to be triangles. They can be like squiggles if you want, like that. But generally in competitive math, you'll usually be talking about similar triangles. And similar triangles have only 3 ways to determine that they're similar for sure, which is SSS, 3 sides, AA, 2 angles, and SAS, side angle side. So SAS, if you have 3 sides of a triangle, you can completely determine everything about the triangle. For example, if I give you a 3, 4, 6 triangle, if you have a 3 and you have a 4, you can the distance between these 2 points is only 6 for exactly 1 triangle. You can't have like 3, 4, and 6 with a different angle here. No, you can only have like 1 type of triangle. And that's why side, side, side is enough to determine the triangle. So, but to use it for similarity, you need the 3 sides to be in the same ratio. They don't have to be the same. For example, 3, 4, 6 is similar to 12, 16, 24 because all these sides are just multiplied by 4 to go from 1 triangle to the next triangle. And similarly, 6, 8, 10 to 3, 4, 5, you just have a 1/2 dilation. Now moving on to angle, angle. Angle, angle is pretty neat because if you're given 2 angles, you can actually find out the 3rd angle. So a side, 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 you need to be given 3 things, but for angle, angle, you only need to be given 2 numbers, and then you can just find out the 3rd number yourself. So if you're given these 2 angles, then it tells you the triangles are the same, or the triangles are similar. You don't know they're congruent because you can rescale the triangle, but you know they're similar. And then the most tricky one is side angle side. Here you're given two sides and then the angle in between them. So as long as the side ratios match and the angle is exactly the same, then you get side angle side. So one reason why side angle side works is because with these two sides and this angle in between them, you can actually find out what the third side is. The method to do that is called the law of cosines, whether you know it or not. And that kind of makes side angle side and side equivalent. So both ways completely uniquely determine the triangle. But what happens if the angle is not between the two sides, you ask? Well, you get something called SSA, which doesn't work. And the reason why is shown in this diagram. If you're given angle A and you're given AB to CB, that's side ratio, there's actually two types of triangles that can work here, because both triangles A, B, C sub 0, and triangle A, B, C sub A fit the conditions, which stems from the fact that if you want a point B here and a point C on this line to have a fixed distance, there are two possibilities for a point C, which is denoted by the circle of all points a certain distance from B. So that's kind of a bummer. You can't guarantee that the two triangles are similar with SSA. But actually, sometimes you can use SSA if you add an extra condition, because SSA gives you two possibilities. So you just have to give a condition to eliminate one of the possibilities, and then there's only one possibility. So what ways are there for this to work? Well, the first possibility is to make sure that there's only one possible value for C on this line. And the only way for that to work is if C is a foot of an altitude. Then the circle just becomes tangent to this line, and there's only one possibility for C. So this first possibility is altitude, or in a right triangle. So if you have a right triangle, you can use SSA. Then the second method is, if you keep expanding what BC is, then C naught gets closer and closer to A, until eventually when you make BC greater than AB, you get this weird situation where your triangle becomes like outside of your original triangle, which means you get an obtuse angle. So this triangle no longer fits the angle A condition. So this thing doesn't work. So in that case, when you're given BC is greater than AB, there's only one triangle, which is going really far in that direction. But there's actually a third way as well. If I just rewrite this for a second. And the third method is if you're actually told whether this angle is obtuse or acute, because one of those angles is obtuse, one of the angles is acute. So if you're told which one it is, then you know which one it is. So many problem descriptions have a condition like triangle ABC is acute or triangle ABC is obtuse with the obtuse angle at B. If you're given a condition like that, then SSA becomes a possibility because you're limiting SSA down to one of the two. That's when SSA works, but don't tell your teacher, oh, I heard SSA works, because it doesn't always work. So you have to be very careful with it. Okay, so now let's talk about congruency right now. Congruency is pretty similar to similarity, but there's a few important differences. First off, in similarity, I talked about making sure the ratio of the sides is the same. Like a 3, 4, 5 triangle would be similar to a 6, 8, 10 triangle, but they're not congruent. In congruency, you remove the ability for you to rescale the triangle. Now you're just down to like rotating and moving. So it's the congruency conditions are changed. SSS is kind of the same, except you remove the ratios. SAS is also the same, you just remove the ratios of the sides. But angle is changed. Now we need angle, and the side. So we need at least one side of the triangle, because if you're only given angles, then you could still rescale the triangle and keep the angles the same. So you need this one last side somewhere in the triangle to kind of give you congruency. Yeah, that's congruency. Congruency is not really as useful as similarity in solving problems. Okay, here's an important thing about similarity. If you're given two similar triangles or shapes, there's this important theorem or result that you can actually find out the ratio of the areas based on what the ratio of the sides is. And it's in the quadratic ratio. So this should kind of make sense to you. If you draw two squares, one with side length x and one with side length y, we know that the area of this square is x squared, and the area of this square is y squared. So the ratio of areas is x squared over y squared, and the ratio of the sides is x over y, then you square it. So that fits this theorem. And this kind of works out more generally for any similar shape. Let's give some more examples. If we have a triangle, the 12, 13, 14 triangle, and if we compare this to a much bigger triangle, that's 24, 28, 26. If you compare these two triangles, they're similar by SSS. The ratio between the sides is 2. So the ratio between areas, area ratio, is 4. And this doesn't even have to be with polygons. It could be with like strange squiggle shapes. I mean, these aren't really similar because of my bad drawing, but this theorem at the top still applies to them. Okay, let's move on to some more results. So this is a cyclic quadrilateral, which is a quadrilateral inscribed in a circle. Based on Luke's angle chasing class before, you should be able to find out that some of these angles are equal, and therefore some of these triangles are equal. I want you all to draw this on your paper and try and find out which of these triangles are similar. I'll give you like a minute for that. Yeah, I think that's enough time. So from Luke's angle chasing class, you guys should know that this angle and this angle are the same because they both face this minor arc AC. And the same thing is true here. This angle is equal to this angle because both those angles face this arc DB over here. So what that tells us is if you look at triangle ATD, and triangle CTB, both these triangles actually have shared both of these two angles. So these triangles are similar by angle. So triangle ATD is similar to triangle CTB. And remember, I'm actually paying very close attention to the order of these points. So A and C are both first because angle A, this angle at A and this angle at C are equal here. That's why I put this order. And you can do a similar thing for these other two small triangles. This angle is equal to this angle, and this angle is equal to this angle, which tells us that triangle ATC is similar to triangle DTB. And these two pairs of similar triangles will come up a lot in math or geometry in general. Okay. So when you finally see similar triangles in the math problem, what do you do with them? So what you do is you usually use the length ratios of a triangle. You see over here to the right, I have this equation here. And this is because if you have one ratio, the ratio of like dilation between two triangles, that means each individual side is scaled up by that same ratio. So that gives you actually three equations, or like three parts of this massive equation that are all equal. And normally you won't have to use all of these three parts, you usually just have to use two parts. But if you're having trouble or struggling, or even if you're not, I encourage you to write out this full equation because it'll help you see things clearer, even if you think you don't need to do it. Okay, now let's get to some actual problems. For the rest of the class, we'll just be doing problem after problem. Okay, so this problem comes from 1995 AHSME. And I wrote the problem conditions up here. You have this diagram, like two right triangles embedded in each other. You're given AC is 6, DE is 4, BC is 8, which is this side. And we're given that these two triangles are 90 degrees. And the question wants you to find out what is DB. So you guys should try and do this on your paper for like a minute or two. It seems like some people are done, so I'm gonna go ahead. So the first step is you have a right triangle and you know two of the sides are 6 and 8. So immediately you can find out what AB is. So AB is 10. And that's because triangle like ABC is similar to a 3, 4, 5 triangle. So whenever you spot like 6, 8, or any two numbers in the 3 to 4 ratio on a right triangle, immediately think to 3, 4, 5 triangles. So that gives you what AB is, 10. And now we realize that triangle ABC is similar to triangle DBE. And why is that the case? Well, it's because of angle. Both these triangles share this angle right here at B, and they both have a 90 degrees. So this is true by angle. So what that tells us is if we're going to write out the full equation, regardless of whether we need it or not, we get this. BC over BE, AC over DE. And if you ask how I got that so quickly, this first one is from me taking the first two letters here and the first two letters here. That's how I got AB and DB. And this second term is me taking the second two letters and the second two letters. And this last term is me just taking the first and third letter and first and third letter. So that's how you can come up with this similarity ratio pretty easily. So if we try and fill out what this is, we get AB is 10, DB we don't know. DB is what we want to find. BC is 8, and BE, we don't know what BE is. And AC is 6, and DE is 4. So we actually like these two terms a lot. So this gives us that DB is equal to 10 times 4 over 6, which is 20 over 3. So 20 over 3 is our answer. Okay, so this was like a pretty basic, pretty easy similarity problem. We'll get into more complicated questions. Okay, this one is MATHCOUNTS 2020. It's from chapter and it's on the target round. Some of you may know this problem if you're actually in middle school right now and did MATHCOUNTS. So you're given a right triangle and you're given 3 similar shapes. These shapes are no longer triangles, but George Washington faces, like these shapes over here, but they're similar. And you're given 2 lengths of this right triangle, and you're given the area of this big Washington face, and you're asked to find the area of this small Washington face. So I'll give you like a minute as well for this. Oh, and by the way, I know it's a target round, so usually you would be allowed to use calculators, but I want you to solve this problem without using calculators. That's my challenge. So I measure whether you're done or not based on whether you're looking at the screen. So when you finish, just look up at the screen. I don't know you're done. Okay, some of you seem to be done, some of you aren't. I'll just start talking. You can keep trying if you're not done yet. So the first thought that some of you may think is, okay, I have 2 sides of a right triangle. Hey, I can find the third side via Pythagorean theorem. Okay, I have 6.2, I have 9.3, and that means this third side is, square root of 6.3 squared plus 6.2 squared plus 9.3 squared. Oh no, I have to square stuff. Okay, let's do 62 squared. I think it's like 4. Let me do some like mental math skills. 2. Oh no, this is too hard. Maybe 3 squared. Oh, that's even harder. Okay, this is not the way you do this. Don't do this. So I told you not to use a calculator for a reason. If you're in the target round with a calculator, you may actually be able to do this calculation. And even if you're not, you would be able to do it, but it's a waste of time and you shouldn't do it. You can actually use Similarity to not have to do that. So this right triangle, this 6.2, 9.3 triangle, is actually similar to this triangle, 2, 3. And the ratio is 1 over 3.1, right? Because 6.2 is just 2 times 3.1, and 9.3 is 3 times 3.1. So these two triangles are actually similar. And this third side, we can calculate much easier. Square root of 2 squared plus 3 squared equals square root of 4 plus 9, which is 13. Okay, that's much easier. But this is a different triangle, right? Can we actually use this triangle for this problem? And the answer is yes, because when we're trying to find the area of the small profile, we actually only care about the ratios of the sides. If you remember, we had area ratio equals side ratio squared. So we actually only care about the ratio of sides. So the area ratio is big face over little face equals the ratio of the sides. And the ratio of the sides of the big face to little face, so I'm going to look at this face over here, which is the height of the big face, to this length over here, which is the height of the little face. And what that's going to be is the hypotenuse over small side. So normally to calculate these sides, you'd have to find the length of this hypotenuse here, but that's why I said you don't actually need to do. Because this right triangle is similar to this 2, 3 root 13 triangle, this side ratio is actually square root 13 over 2. So what this tells us is that little face, oh shoot, okay, the little face is equal to the big face times, you have 2 over square root 13. And remember, we have to square this because it's side ratio squared. That's equal to 25 times 4 over 13, which equals 100 over 13. And that's our answer. Okay. Okay, now let's get to some harder problems. Okay, this is a AMC 10A question. So most of you are probably in middle school, so you won't take AMC 10, but you should start preparing early. Okay, so this question is, you have this rectangle, you draw BD, you draw E and F such that E and F trisect the segment. These are all length 1. And the question is, you're also given AB is 6. You want to find BP to PQ to QD, that long ratio. So you all should draw the diagram and try it yourself. And once again, look up when you're done. Okay, so this problem may be a bit hard for you, so I'll be putting some hints also to kind of speed this up. So the first hint, kind of obvious, use similar triangles. But if you guys want like a second useful hint, I can kind of help you figure out what the similar triangles are. And the hint I can give is if you have two parallel lines and you draw two transversals crossing through, then these two angles are equal and these two angles are equal. You guys should have learned this with the angle chasing class. So then this actually gives us two similar triangles. And you can apply that here with AB being parallel to BC. Okay, let's write down what similar triangles there are. So using this hint number 2, we can first look at this small triangle BPE. Triangle BPE is similar to what other triangle? Well, applying here, we get this big triangle APD over here. APD. And, well, okay, I actually made a mistake here. I wrote it in the wrong order. So this angle at B here corresponds to this angle at D. So I really should write D over here and A over here. And writing our length ratios, what do we get? We get BP over DP is equal to PE over PA, which is equal to BE over DA. So the one that's the most useful will be involving BE, which we know the length of, and also BP, which is part of the ratio we want to find. So what this gives us is BE over DA, this is equal to 1 over 3rd, because BE is 1 and DA is 3. So that tells us that BP is equal to 1/3 DP. So here's where I can kind of talk about strategy. So when you want to find the ratio of 3 things like this, you have to find all 3 in terms of one common variable. Then you can cancel out that variable later on as it's a ratio. So the common thing I'm going to relate all these 3 sides to is BD, because BD makes the most sense. Like here, I've already related BP to DP, but DP doesn't make much sense. It's not as nice as BD. So instead, I'm going to do this. BP is actually 1/4 of BD, because if it's 1/3 of DP, then you have like a 1:3 ratio, which means the total thing is like 1:4. Okay, and now let's do the same thing we want to do the same thing for like QP and QD. here's other strategy. Here's another strategy. So QP is not actually part of a nice triangle. Like it's part of AQP, I guess, but AQP isn't really similar to anything. So we're not able to actually directly find QP like that. Instead, what we can do is, let me just rewrite this. We can actually find QD in a similar manner. So if you look at triangle ADQ, there's a triangle that's similar to it. Can you guys see what it is? So let's just start matching angles. So angle A, angle DAQ, it matches with this angle because of parallel lines. And this angle matches with this angle because of parallel lines. So we get triangle ADQ is similar to triangle FBQ by AA. So once again, we can write out the length ratios. We have AD over FB is equal to DQ over BQ, which is equal to AQ over FQ. And here, these two are going to be the important ones because they involve what we know and what we want. So we know AD is 3, and we know FB is 2. So we know DQ over BQ is equal to 3 over 2. So what we have here is that if DQ is like 3 times something, which I know as K, then this QB is 2 times K. And what that tells us is DQ is actually 3/5 of the total dB. Okay, so what does that mean? So we know BP is 1/4 of the total. We know DQ is 3/5 of the total. So then how are we going to find out what QP is? Okay, so we know that the sum of these three, this plus this plus this, need to equal the total BD, because you know BP plus PD plus QD just gets you a whole BD. So this is actually 1 minus 1/4 minus 3/5 BD. And what that means is, if you write out this ratio, multiplying all three of these terms by the same constant does not affect the ratio. So we can get rid of BD. We just have 1/4 to 1 minus 1/4 minus 3/5 to 3/5. And if you multiply everything by 20, you get 5. Over here, you get 12. And over here, you get 3. And that's a ratio. Okay, how was that? Was that okay? Hard? Okay, let's go into the next problem. Okay, this is like a harder AMC 10A question from 2003. So you know, we can work through it. It's okay. I can give some hints. So this problem, you're given this rectangle, and you're given points H and E. Point H is given such that HC is 3, so it's a 3:6 ratio, and E splits DA into side lengths like 4 and you can figure out here as well what EA is. And the question is find out GF. Okay, you're also given this is 8. So I want you guys to solve this as well, but I'll give you the similar triangles first so you guys don't waste too much time. So first off, we can just do the right triangles. The right triangles are pretty easy. Triangle GFE is similar to triangle CDE because this angle is equal to this angle. That's the first right triangle similarity. And we can also find a second right triangle similarity if we extend this. If you extend this to point I, we can have triangle GIC. Not GIC, GIH is what I want to do. GIH is similar to triangle GFA. And you can find a lot of other similarities in this triangle, in this picture as well. For example, you can even use this small triangle here. Triangle GCH is similar to triangle GEA. So what your task is going to be is to use some of the similar triangles in this diagram to actually find out what GF is. So go do it. So I'll write down some hints so you guys can kind of progress faster. Okay, I'm gonna get started. So EA we know is equal to DA minus ED. And we know what DA is from looking at side CB. It's a rectangle, so CB is DA, which is 6 plus 3, which is 9. We subtract ED from it, which is 4, we get 5. So EA is 5. And using that length is 5, that can actually tell us certain things. Okay, so our next step 2, is HA. So HA, we look at this 6, 8, 10, the 6, 8, 10 triangle here. So that gives us that this is 10. Again, this is the 3, 4, 5 triangle, just scaled up by 2. Whenever you see 6 and 8 in a right triangle, their length 10. Boom. Okay, so now our third step is the first kind of like tricky step. Combination step is what you can call it. You have to use both hint 1 and 2 to find out what GH is. How are we going to find GH? Okay, to find GH, we're going to use this the similarity right here between this black small triangle, and you can extend it down further. So what that tells us is GH over GA is equal to CH over EA from the similarity ratio of this similarity. That tells us that GH is over GH plus 10 is equal to 3 over 5. So when you want to find out what GH actually is, you have 15. Okay, so now we have GH is 15. And this final step is to find out what GF is. Okay, so yeah, there's only one similarity left. Let's see if you guys can see it. So the last similarity ratio we're going to use is over here, GFA and ABH. And that is this really big right triangle, the biggest right triangle, and this black right triangle over here. those two triangles are actually similar. And if you want reasons why, we get this entire angle is equal to this angle over here at A. And then you have a right angle. So by angle, those are similar. What does this tell us? This tells us that GF over BA is equal to GA over AH. We know what GA over AH is. So from hint 3, we get that GA is 25. And we know that AH is 10. And if you go in the other direction, GF, we don't know what that is yet. But we know what BA is. BA is 8. So this tells us that GF is 25 over 10 times 8. And you know, you can do that yourself. So you get 20 as the answer. Okay, so I did it in this method for you, but there are actually different ways to do this problem. As you see, there are so many similarities we didn't actually use. So there are other ways to do it. One way would be to try and calculate IH or IC, which is equal here. That would also help you solve the problem in many ways. In similarity problems, oftentimes, one of the biggest problems is finding out which similarities to use. And in this case, almost any way you did it works, but sometimes you'll actually have to think really hard about which ones to actually use. Okay, so this is a problem from Brilliant, and it's a similarity problem. So you're given three sides that are parallel to the triangle sides. And same thing for MN as well, it's parallel to AB. And then it tells you the area of these three smaller triangles. The area of this one is 4, the area of this one is 9, the area of this one is 49. And it asks you to find the area, the total area of the triangle. So I'll give hints as well, because this may take a while otherwise. Okay, so if you remember a while ago, I told you that the lengths of the side, the ratios of the sides of similar triangles, when you square that, you get the ratio of the areas of the triangles. So here, they give us the areas, but that actually tells us the ratio of the sides as well. You just have to take the square root. So the ratio of the sides is, this is equal to, we square root the areas. And this works because EP, DM, and PR, the three sides I put, are actually the corresponding sides of a triangle. Like I can't just pick any random 3 sides of these 3 triangles and it equals this. I have to pick corresponding sides. But these are corresponding. So we get this is equal to 2, to 3, to 7. Okay. So now that we have the ratio of these sides, we get that EP is 2 times something, which I'll call K. We get the DM is 3 times something, again K, and PR is 7 times that same something. So my hint number 2, I asked you what is CA over PR. We get that CA over PR. To find CA, we note that CE PD is a parallelogram. Because all these sides, opposite pairs are parallel. So actually what that means is that DC is equal to EP. And similarly, MPRA is a parallelogram. So we get that MA is equal to PR. So if you go back over here, we can split CA into CD plus MD plus MA and all over PR. But if you look at what we got from the parallelograms over here, we can turn CD into EP. MD is fine as it is. And we can change MA into PR, all over PR. And from the ratio of the sides over here, this is actually just 2 plus 3 plus 7 all over 7, which is 12 over 7. So now, finally, we can actually find the area of triangle ABC. We know triangle ABC is similar to triangle PRT. Because as lines are parallel, we have all these equal angles, which is why all these triangles are similar to each other. So this tells us that the area of triangle ABC, which I denote as bracket ABC in bracket, is actually equal to the area of PRT times the side ratio squared, which is 12 over 7 squared. We know that area of PRT is 49. So this actually just gives us 144 as our final answer. Okay, so we're almost done. So next is a problem, but it's a bit different from normal computational problems. So I'll just be showing you a cool proof I know of the angle bisector theorem that uses similarity. So the angle bisector theorem states that if you have a triangle and you have an angle bisector bisecting one of the angles, it splits the third side such that C over M equals B over N. The ratios are kind of equal. And if you notice, these side ratios kind of look similar to similar triangles. And we can end up actually solving or proving this theorem using similar triangles. But if you just look now, there are no similar triangles. While they may share one angle, they don't share any other angles. So we have to construct our own similar triangles. And we do this by extending these sides of the triangle. And then if you look at AD, we draw lines that are parallel to AD. From B and C. Okay. I'm going to call this point over here E. I'm going to call this point over here as F. Okay, so I define these two lines to be parallel to AD. So that means that this green angle over here is actually equal to these angles as well. You guys should know this by parallel lines from the angle chasing class. But what this also tells us is, since AD is parallel to EB, and we have this transversal, this green angle over here is actually equal to this angle over here as well. And similarly, you have two parallel lines and a transversal, so this angle is equal to this angle. The name of this is alternate interior angles. So now if you look at triangle EAB and triangle FAC, these triangles are both, guess what, isosceles, because you have two equal angles inside the triangles. So what this tells us is that EA is also C and AF is also B. And now this is starting to look pretty nice. Okay, let's do some similar triangles now. We have triangle ACD is similar to triangle ECB. That's this triangle over here. And then you kind of expanded about C to get this whole big EBC triangle. And what that tells us is we have this situation here. CBMN. And these similar triangles tells us that C plus B over B is equal to M plus N over N by the similarity side ratios. So this is so close to what we want, but it's not quite there yet because you have plus signs. You have like, you know, C plus B. You don't have like C plus B over here. But we can actually get rid of that by subtracting 1 from both sides. If you look at C plus B over B minus 1 equals M plus N over N minus 1, then this left-hand side just becomes C over B, and this right-hand side just becomes M over N. So we get that C over B equals M over N, which is equivalent to this up here, and that proves the angle bisector theorem. So yeah, similarity is very powerful. You can do many things with it, and you can get much more complicated problems than what I showed. But hopefully you guys have learned a lot today, and this is going to be the end of the class. Thank you all for coming. Bye-bye.